somebody has come in here since I was here on Monday with you and shut everything down. And they've done some stuff to the machine you couldn't fix right away. But anyway, we're up and running now. Okay. First thing I'd like to do, everybody got the email I sent for the neutron flux lab for next Tuesday. I'd like everybody to get back to me today or tomorrow by 1 o'clock, because when I leave URI tomorrow, I want to let them know how many were coming and if we're going to need 1 session or 2 sessions. Because as soon as they're finished with us on Tuesday, they're out the door for the Thanksgiving weekend. So I'm not going to tell them Monday afternoon, oh, by the way, I need a second group. Okay. I guess the first one I'd like to do today for quiz is reactive theory. Do any of you want to put up your solutions for extra credit? If not, I'll do mine. No takers. Okay. So we'll do mine. I gave you some various information. And I'm telling you that we're going to have a rectangular solid. And we know the flux equation for a rectangular solid is flux, which is a function of x, y, and z. Again, these three are the independent variables. Flux is a dependent variable. Is equal to flux max, cosine of pi x over x of 0, cosine of pi y over y sub 0, cosine of pi z over z sub 0. In our particular case, for our specific case, this comes out to be and then what I've asked you to do is to find the flux at a particular point. And the point I gave you was -5, -6, and -12. So if you go in and throw those values in, and remember when you do this, that pi here is equal to 180 degrees. When I do this, this becomes the cosine of minus 45 degrees. This becomes the cosine of minus 43.2 degrees. And this becomes the cosine of minus 72 degrees. If I then do that calculation, this comes out to be 0.707. This comes out to be 0.729. And this comes out to be 0.309. Okay. If I multiply this times this times this times the flux max, I have the value of the flux at that specific point to be 1.115 times 10 to the 17th neutrons per square centimeter per second. Fairly straightforward. Any questions on that part? Okay. I'm going to erase part of this. I want to save this part. And then I go back and ask you to find the neutron current density in the plus z direction at our point of interest. Or instead of putting this, I could have put my little subscript 0 there, because remember, we're evaluating at the point of interest. This is the point of interest. And we know that that's equal to the flux at that point divided by 4. If this is a plus and this is a minus, d over 4 times the partial of the flux with respect to z, because that's the neutron current density we're looking at, evaluated at our point of interest. This value we just found, which is 1.115 times 10 to the 17th. Little d from up above was 1.2 centimeters. We need to find the partial of the flux with respect to z. So if we go back, we remember that the flux is equal to flux max cosine of pi x over 20, cosine of pi y over 25, cosine of pi z over 30. Might as well throw this value back in. This was 7 times 10 to the 17th. So when we take the partial with respect to z, again, we're taking a partial with respect to z, realizing that we have both x, y, and z. So when you do this, you're taking the partial on this side also. And remember, everything that does not have a z in it, we treat as a constant. So this becomes 7 times 10 to the 17th times the cosine of pi x over 20 times the cosine of pi y over 25. When we do that guy, it becomes minus the sine of pi z over 30 times the partial of what's inside, which is pi over 30. We throw in the points of interest. This is minus 5. This is minus 6. This is minus 12. Okay. So this is exactly this. This is exactly this. That's why I encourage, when you do this, put in your value, convert it to an angle so you can see what that angle is, then take the cosine of it to come up with a value. Because you're probably going to find yourself going back to use these values again, and it just saves you having to recalculate this. So this is going to be now minus the sine of minus 72 degrees times pi over 30. I had this value come out to be 0.951. I had this guy come out to be 0.105. So when I multiply this times this times this times this times this, I have this, and I had that value come out to be 0.36 times 10 to the 17th. So if I go back up here, that value here becomes 0.36 times 10 to the 17th. And then when I do this algebra, I have this final value come out to be 0.279 minus 0.1082. So my final answer was 0.171 times 10 to the 17th neutrons per square centimeter per second. Any questions on how you do that? Everybody good with that? Because trust me, you're going to be doing this on your take-home exam, this type of thing. Okay? If there's no questions on that, then I am going to erase all of this. I'll leave this value here for a second. Then I ask you, what is the neutron current density in the z direction at our point of interest? Okay. There's two ways you could have approached this. You could say, I know this is Jz plus at that point minus Jz minus at that point. And what you're really doing when you're asking for the neutron current density in the z direction, remember, if I look at a three-dimensional solid being part of this room, if we're looking at the z direction, I'm establishing my little window right here. Is 1 centimeter by 1 centimeter. And I'm looking for how many neutrons are going through this little target area, which is 1 square centimeter per second. If we're looking at fuel and moderator that are behind the blackboard, that are generating neutrons that are coming through the little window going in this direction, that is my Js plus, because this is the plus direction. And if I look at all the fuel and moderator on this side of the window and say what's going through to behind the blackboard, that then is Jx minus. If you're a glutton for punishment, you could go back and say, okay, I know that this is I know this guy so I could go back. We've already done one of these, but you could go back and do the other, put one of them in here, put the other one in there, and then do that algebraic addition, because again, these vectors are acting along the same axis. Or you could realize that the neutron current density net in the z direction is equal to minus d, which is a diffusion constant, times the partial of the flux with respect to the z evaluated at the point. We have already calculated this with the last problem, and we know that little d is equal to big D. So D is equal to little d over 2. We can throw the values in for that. And this was 1.2 divided by that. And the other number we had before was 0.36 times 10 to the 17th. So my final answer is minus 0.216 times 10 to the 17th neutrons per square centimeter per second. So what that means is for our little window that we have at our point of interest, and our point of interest was -5, -6, and -12 in this rectangular solid, the net neutron current density in the z direction is minus, so that means it's going more in that direction, and that is a differential. So that is the net neutron current density in the z direction at the point of interest. Any questions on that? Okay. And now to sort of shift stream here. I went back to our beryllium, uranium 233, uranium 238 mixture. And I said, what is the value going to be for R sub G if placed in a sphere shape? Remember before we've put it in an infinite slab, we've also put it in a cube. So now I'm asking you to put it in a sphere. We know that Buckling squared has a unique value for a sphere, and it's equal to pi over r sub 0 squared. So r is equal to pi over b. In our particular case, our b was 0.206 when we went back to this problem. So that r was equal to 15.25 centimeters. If you look at how the flux is in a sphere, there's an Rg value, and then it goes a short distance d, so that this value from the center of the circle to the extrapolated distance at the boundary where the flux goes to 0 is r sub 0. So r sub g is equal to r sub o minus little d. And our little d from before was 0.91. We just found this at 15.25. So Rg for the extra credit was 14.342 centimeters. And again, our original buckling value we got from this mixture. And remember when you just looked at the materials, it was equal to this. And this value is constant as long as you have the same grouping of fuels and moderators. You can then put it into any shape, and you just have to select the appropriate buckling expression for that shape. And again, the only other one the book showed you was for a cylinder, and you had the buckling value there, but you can't really utilize that because you don't know how to determine or evaluate or find Bessel functions. So I'm not going to give you that type of thing. Any questions on that quiz? Okay. I'd like to lecture a little bit more today, and then maybe what I ought to do is do a little bit of review first. What would you like to review? On Monday, I'm going to give you a take-home exam for reactor theory. It's going to be due after Thanksgiving, and I typically give you till the Wednesday after Thanksgiving. So you have over a week to get that done. You can spend as much time as you want on it, but again, I require that it's only your own work. You don't give or receive any help, and I expect that usual honor statement on the exam. I'm going to give you multiple fuels, multiple moderators, and then you're going to have to find K infinity. You're going to have to find buckling. You're going to have to find other values, and then I'm going to have you put it in a shape that I am giving you. And then you're going to have to find various parameters about that. My guess is if you've been following things, because it's a lot of number crunching, it's going to take you around 5 hours if you're really keeping up to snuff on things. If you haven't been keeping up to snuff, it's going to take you longer to do it. One of the things I typically ask when you turn in the exam, I also ask you to tell me how much time you spent on the exam. And I've had people tell me before they spent like 20 hours or whatever. You can spend as long as you need to do the exam. But is there anything in particular you would like to review? If not, I'm going to lecture a little bit more today on reactive theory, and what I'm going to do is look at other things we could do, such as reflectors, blankets, look at taking it from one group theory, because the only thing we've done thus far is one group theory, which we assumed everything was thermal. So we're going to look at multi-group theory, how you would solve that type of thing. But any questions on what we've done so far that you'd like to review for the take-home exam on Monday? Everybody's good.
Can we maybe work another problem, like from scratch?
Well, we could do one, but it could potentially take quite a while depending on what we do. Let me see if I have anything in the back of the book that might work. Okay, I'm not sure this is going to work. I'm not sure I have everything that I need here from just looking at what's in the book. But I might not necessarily work this problem through to completion, but we can at least talk our way through it. Let's say I gave you a mixture where you had 180 moles of sodium (23), per mole of fuel, and that fuel was 10% enriched with plutonium-239, with the other 90% being uranium-238. One of the first things I might ask you is, what is K infinity? K infinity is equal to EPF nu. Again, remember, I always draw like an imaginary line between them, Everything on this side is fast or epithermal. Everything on this side is strictly thermal. I would have to give you a value for epsilon. So if we say that this is homogeneous, then that means that's automatically defined as 1. If we look at the resonance escape probability, this is e to the minus. And again, whenever you're working these, I would suggest you go back and look at where I recommended you paperclip the page, because you're going to go back and using it, which is page 251. This is equal to minus N238 over squiggle, macroscopic cross-section for scattering, times I effective. In order to get in to use this, we're going to have to do mole ratios. You can pick anything to be your common denominator, but again, you typically pick the one that's the smallest. So if we look at the ratio of sodium to plutonium, that's 180 divided by 0.1, because we have 1 mole of fuel, of which 10%. So that is 1,800. If we look at the ratio of uranium to plutonium, that is 0.9 divided by 0.1, so that's 9. If we look at the ratio of plutonium to plutonium, that's 0.1 divided by 0.1, which is 1. So the next thing we need to calculate to get here is I effective. I effective is equal to 3.9 times the macroscopic cross-section for scattering divided by N238. All of this raised to 0.415 value. We know that for the macroscopic cross-section for scattering, this is also equal to N times the microscopic cross-section for scattering, but we have to include this calculation for every material that we have. We have 3 materials, so this sigma S has 3 parts. So it's going to have a part due to sodium times the scattering for sodium plus a value for uranium times scattering for uranium plus N for plutonium. Again, that's the scattering value. And what scattering values are going to use? We're going to use epithermal, because everything on this side is considered to be epithermal. So this value, and this value from the back of the book would be the epithermal value. We know we're going to have this divided by this. But we don't have number densities. We do have mole ratios. So if I go back here and divide everything by N plutonium, N plutonium, N plutonium, N plutonium, we have these values we can substitute in here. We can come up with this value. And again, I have you typically whatever this value comes out to be is that value. So I have you save that, because then if you notice, this is a reciprocal of this. So whatever this number is, you can just invert it, and you already have this. Calculated that value. That leaves you calculating squiggle. Squiggle is supposed to be for your entire mixture. But we know that when we calculate squiggle, squiggle is primarily due to the moderator. In this case, we only have the one moderator. So this is going to be 2 over A plus 2/3. My moderator is sodium, so that value is 24. You could calculate them for the fuels, but they're going to be so small that for the mixture, it's essentially just the value for the moderator. Throw that in here, we come up with a value for resonance escape probability. We know that this value must be between 0 and 1. We want this to be as high as possible because we want to keep K infinity as high as possible. So when you get an answer, first of all, you want to make sure it's between 0 and 1. If it isn't, you've made a mistake somewhere. And then hopefully it's a higher value. Next thing you have to do is calculate F, which is the thermal utilization factor. And that's looking at what's happening in neutrons absorbed in fuel by neutrons absorbed in everything. So when you do that calculation, we know we have 2 fuels, so we're going to have N plutonium, sigma A plutonium, plus N uranium, sigma A uranium, divided by everything, which includes these 2 again, plus the moderator. Again, before we can do that, we've got to take it back to our all of these values you get directly from the back of the book. If it is a fissile fuel, which we have for the plutonium, you have to go in the back and look at the absorption value. And that absorption value for 239 is 746 in F, 280 in gamma. So the total absorption is the sum of these barns. Excuse me. That's the value that's going to go in here because that is the total absorption for that fissile fuel. But we know of this probability, this is creating a fission, but this number only create a gamma because that's a parasitic loss. Do that math again, F, when you calculate it, must be between 0 and 1. And this is usually very high, very close to 1, because again, you want to keep K infinity high. The final calculation is for nu, which is your reproduction factor. And nu looks at thermal fission fuels versus all fuels. So we only have one thermal fissioning fuel, which is plutonium. So that's going to be N plutonium, sigma for fission for plutonium, which is the first part of this, which is going to be this 746, times nu, which is a multiplier that you find in that table in chapter 4 that tells you, on the average, the number of new neutrons created per thermal fission. And then you're going to divide it by what's happening with all your fuel, which is going to be N to U, sigma A to U, plus N uranium, sigma A uranium. And again, we need to divide this by our common denominator. Do that math. We'd like this value to be definitely higher than 1, hopefully closer to 2, if possible, or even higher. You've then calculated all parts of K infinity. Throw those all together. You know this needs to be greater than 1 in order to have a chance of being useful, because this being infinite does not count for leakage. Once you have a value for K infinity and you've determined it looks viable, you could go ahead and do the next set of calculations. Next set of calculations, what again I would recommend you do is I recommended that you paperclip a second page in the book, which is page 260, because it tells you how you calculate buckling for any fuel and moderator mixture. So we're going to do and find the volume for each material. We're going to then use that to find the number density for all materials. We then need to calculate the macroscopic cross-section for transport. We need to calculate the macroscopic cross-section for absorption. And again, this is the sum of N times sigma A. This guy is the sum of N times sigma S times 1 minus the average value of cosine, or whatever that particular material is. So in this case, 3 materials, we're going to have to do 3 of these calculations, add them together. Down here, we're going to have to do 3 of these calculations, add them together to come up with those values. And then just following that cookbook, we know L squared is equal to 1 over 3 macroscopic cross-section for transport, macroscopic cross-section for absorption. And then finally, we know that buckling for our mixture is equal to K infinity minus 1 over L squared. And this value, and particularly we're looking at the square root of that, is the buckling. And this is good for any mixture. So then once we have that, then you have to see what kind of shape you're going to put it in. Whatever that shape is, we know we start off with the general diffusion equation. Del 2 flux plus V squared flux equals 0. We have to take the del 2 for a shape, apply that, then solve using boundary and initial conditions. And then when you do, that's going to leave you with a specific flux equation for the shape. It's also going to leave you with a buckling squared value for that shape. If, for example, I told you to put this in an infinite slab, you automatically know that the solution to this differential equation using this modifier, in this particular case for an infinite slab, we know that it's that. We put it back into here, we solve it for boundary and initial conditions, and the flux, which would only be a function of x, is going to be flux max times the cosine of pi x over x sub 0. The buckling, when you do the same thing, comes out to be pi over x sub 0 squared. So you can find this value of x sub 0 because this buckling squared is the same as that buckling squared. Remember, buckling is where you couple materials to shape. If I instead ask you to put this in a cube, this del 2 would become again solving for boundary and initial conditions. This would come out where the flux is a function of x, y, and z. And that's going to equal flux max cosine of pi x over x sub 0, cosine of pi y over y sub 0, cosine of pi z over z sub 0. So this is good for any particular rectangular solid. If we have a cube, we know that x sub 0 is equal to y sub 0 is equal to z sub 0 is equal to back to x sub 0. So again, by using this equation, boundary and initial conditions, we know that buckling squared is equal to 3 of and again, this buckling squared is the same as this buckling squared. This is materials. This is this unique shape we put it in, which is a cube. Likewise, if you put it in a sphere, if you put it in a cylinder, if you put it in any shape you can think of, you don't necessarily have the math tools to do that right now, but you could develop a specific flux equation and the accompanying buckling squared equation for that particular shape. And then once you have that, you're off and running to find flux. You could find neutron current density, any other parameters about what you're doing. One other thing to mention from the quiz that I gave you that I had to go back and adjust the dimension. When we go back and we have looked at the general diffusion equation and we have solved it, and let's say we go back and we pick, since it's the simplest one, let's say we look at the infinite slab. Okay. How do we know that this is a cosine? How come it couldn't be a sine? How come it couldn't be a tangent? How come it couldn't be a Bessel function or any of hyperbolic, tangent, whatever? How do we know it's this? How do we know it's a cosine? We know it's a cosine because we take the general diffusion equation, apply the appropriate del 2 operator, and it becomes, for an infinite slab, d2 flux This is the general diffusion equation that has become the general diffusion equation for an infinite slab. And now we solve this to both find the flux and find the buckling for that particular shape. And as it turns out, when you solve this for flux, if you remember, the value came out to be and then we solve this using boundary and initial conditions. What do I mean by boundary and initial conditions? This is an infinite slab that is filled with materials. We have intentionally set up this dimension to be the geometric width of the materials. The flux we assumed to have a parabolic shape so that it looked symmetrically something like this. This dimension is the width where the flux goes exactly to 0. So here the flux is exactly equal to 0. Here the flux is exactly equal to 0. This little distance here is little d, which is the extrapolation distance. So we came up with our relationship. What else do we know? We know that the maximum value for the flux is at this point where x is equal to 0. Since this is the slope of this equation, we know that the slope is exactly equal to 0 at x is equal to 0. If we come and look at this point right here, which is plus x of g over 2, if we look at the neutron current density going in the minus x direction right at this little window, so we're putting our little window right here, and we're saying, what do we have for neutron current density going in the minus x direction? Let me put it in that direction. And the answer is exactly 0, because there's no fuel and moderator outside this geometric boundary to create neutrons to put it back through the window. But we know this is also equal to the flux at that point divided by 4 plus d over 4 times the partial of the flux with respect to x at that point. So we're looking at the partial of flux with respect to x at that point. So this is pretty much a straight line. So we can look at rise, which goes the flux at this point. The flux here is 0. The run is the width d. So we have all that to help us establish, and again, that's a boundary or initial condition. We're coming up with the values for flux, and we're coming up with the values for buckling. And you do that for any shape that you have. Obviously, the more complex the shape, the more involved this del 2 operator becomes. But I'm not going to give you anything outrageous for your take-home exam. And that's pretty much it. Any questions on our quick review?
Yeah, I have 2 questions, if you don't mind.
Okay.
You said that the value for the average value of cosine phi is for the material itself.
Say that again.
I'm
Now, when you're back for the
right. So that when we have
transport value.
yeah,
Is that what you're asking?
transport value. Yeah, the average of cosine phi. You said that value was dependent on the material. Is that correct?
Yes, if you go back and look at,
And where
Page
is that
2.
in a chart somewhere?
nope,
Okay.
you go back on page 260, and you look at the definition of macroscopic cross-section for transport. It is the sum of N sigma scatter times 1 minus cosine average value in the lab system. So you have this calculation to do for each material. And the sample we had here with the plutonium and the sodium, we had 3 materials. We had 2 fuels and 1 moderator. So there'd be one of these for sodium. There'd be another one of these for plutonium, and then there'd finally be another one for uranium. Do this calculation, add it to this calculation, add it to this calculation to come up with the total macroscopic cross-section for transport.
Right. I
Just
understand
like-
that. I'm just
For absorption. We need to look at the total contributions of absorption. And we have to do this for every material we have in the reactor mix. Does that answer your question?
Well, no, I understand that. I'm just asking, where is it determined what the value of the average value of cosine phi is?
Okay, that was given to you at the end of the last chapter. And let me find it for you real quick. That was on page 237, the very last. And the average value for scattering is 2/3A, where A is a mass. And if you look at above that, it has what is the average value of scattering for, actually make this theta because it's center mass system. This is exactly 0. This is exactly 0 because when you have a scatter, it could go in any direction. It's isotropic, which means it can go in any direction. So therefore, the average value is 0. If we look at this, what this tells us is if you're sitting in the room and you're watching this as it scatters, so the target and the neutron separate, from where you're sitting, we have the compound nucleus. So in the compound nucleus, there is going to be a velocity to the compound nucleus due to the conservation of linear momentum. And because this is 0 and this has slightly to that direction, this is going to be slightly moving in that direction. So then when you have the scatter, and you have the target going off in one direction, and you got the neutron going off in a direction, this total linear momentum must exactly equal this, must exactly equal the total linear momentum on this side. So when you're looking at this one, since this has, if you're sitting here in the classroom watching this, and you're seeing this thing, it would move slightly to the right when the scatter occurs, and you look at these two the original target and the neutron, and you're looking at them, they're going to be heading off in angles, but the net effect to you appears to be that this whole thing is moving slightly to the right. Slightly to the right is a forward scatter. If you remember, if this comes in at 0, anything that scatters on this side is a forward scatter. Anything that goes back this way is a back scatter. So it appears to you that these two are slightly moving to the right, which is a forward scatter. That's why this average value comes out to be 2/3a. And they did the math for you. And the only thing I've really held you responsible for is to be able to use that in that equation for finding transport. Did that answer your question? I hope.
Yes, it did. Thank you.
So you had multiple questions. What else you got?
Are we gonna, on the exam, is there gonna be multiple moderators involved? And how is
Oh, yes.
we deal with that? Is that what we're gonna go over later?
No, you have all the tools you need right now to do it.
Okay. It's
No,
just
it's everything
included in the total volume.
Everything I've given you thus far for quizzes and samples in the book involved one moderator and 2 fuels. So if I increased it, if I gave you 2 moderators and 4 fuels, you could still do all that. It's more work, but you know how to do it. It's the same thing. You start off, you got to get a common denominator. Then you got to find your K infinity value. Then you got to go find all your volumes. You got to find the number densities, then the transports, then the absorptions, and then ultimately leading to K infinity. And then from K infinity, you're going to go through the other to come up with your buckling value for all those fuels and moderators. So if I gave you 10 moderators and 8 fuels, you can do it.
Okay, thank you.
It's going to be more work because you're going to have more math to do, but you know how to do it. Or at least I hope you know how to do it at this point. Any other questions from Ty or anybody else? Okay, I'm going to talk a little bit more about reactor theory for maybe another 10 minutes or so, maybe 15, and then we'll take a break for about 10 minutes, and then we come back. We're going to work the nuclear materials science problem. And again, if anybody wants to put that up on the board or their solution up on their computer for extra credit, let me know. Otherwise, we'll do mine. We'll go through that, and then we'll do a review there because you're going to have an in-class exam on that on Monday, and that exam is going to be on bending moments. So let me talk a little bit more about reactor theory. Okay. Let's go back to our infinite slab because that's the easiest one to discuss. Okay, we have our basic infinite slab. We have all the fuel and moderator placed in this red hatched area. It has a geometric width of x of g. It has an overall x of 0 where the flux goes exactly to 0. This is the shape of the flux equation, which is flux max. That's a cosine of pi x over x of 0. So this equation is the shape of that curve. And we know, since we have this boundary, there's nothing out here to generate any neutrons to come back in to help us have more fissions. So if you would, everything that's leaving here is lost. It's lost on this side. If you want to call it leakage, that's fine. It's going out this side, that's also leakage. If you look in the z direction, because that goes to infinity, both directions, and y, because that goes to infinity both directions, there is no leakage in that direction. But you say, gee, I want to cut down on that leakage. And I also want to try to increase the reactions that are going on inside my reactor. What can I do? There's several things you can do. Okay. We can look at either a blanket or a reflector. The simplest one of these is a reflector. And what you do is you place at the outer edge of this, and by the way, since this is just as fuel by itself, this as is called a bare reactor. We could put a material of some thickness R on both sides, and if we make it a reflector material, this reflector material is only moderator, or I can make it plural, moderators. You know, when you place it around the outside of our bare reactor core, what happens? Neutrons that are leaving here come into the moderator, and the moderator scatters them, and some of those scattered neutrons turn around and go back into the core that can produce another thermal fission. So you're actually putting a physical amount of material around the bare core, and that's a reflector. What happens then? The overall flux equation in the inside is going to increase because we have more neutrons coming back in. So this equation is going to move up. There's actually going to be a flux equation in the reflector between this wall and this wall. So we have a flux in the core, we have a flux in the reactor, and again, when it reaches the boundary, it's going to leak out to a new point where the flux goes to 0. This will be a new little d for extrapolation distance. This little d is related to the reflector material. It is not the little d that you got back from looking at this core. So when you do that, and typically what you do is you just use reflector material, which is some moderator material, which could be carbon, beryllium, some mixture, You could use water. There's any number of things that you could use. That's a reflector. Okay. Some points to note is you have a separate core flux. You have a separate reflector flux. And you know that the core flux exactly equals the reflector flux where? Anybody want to guess? It exactly equals each other at the boundary. So it's exactly right here and exactly right there. Because you cannot have a discontinuity between fluxes. So you're going to get the flux in the core the same old way we did before by going back to the general diffusion equation. Except this time, you're looking at the flux in the core, and this buckling has to do with materials that are in the core. When you go to look and see what's going on with the flux in the reflector, you're going to go back to the same equation, general equation. Now we're going to be looking at the flux in the reflector, but you're only looking at the materials that are in the reflector to create that buckling value. This little d is determined by the reflector material. If we went back to this outer boundary for R, and we looked at putting a little window there, and we said, what is the neutron current density going in the minus x direction? There's no fuel, moderator, anything out here to make those neutrons go back through the window. So this again is exactly equal to 0. And what is that value? It's going to be plus x of g over 2 plus the thickness of my reflector. So you're going to end up actually solving a set of simultaneous equations because you're going to have one set of equations for the core, another one for the reflector. Do I think you can do that right now? Probably not, but you can understand this concept. Okay. Now, what else do we have in our exposure? We have blankets. Okay. A blanket is made up of fuel and moderator. And typically, we use spent fuel. And we do the same thing. We have, I'm going to erase this other. So we have our bare core with the flux in the core, which we can find by using the general diffusion equation. And again, I'm using the infinite slab. Now we're going to put around this our blanket material. Okay. The blanket material is made up of both fuel and moderator. So when the neutrons leak out of the core, the bare core, when they go into here, two things can happen. They can cause a thermal fission, create more neutrons, and some of those neutrons will go back into here to create more power. The moderator could scatter some of these back into here. So both of those are positive attributes. And as you might expect, since this and this are separate from this, there will be a flux in the blanket. There will be a flux in the blanket. And again, it's going to have its own unique shape. And because of these going back in, this overall flux in the core is going to increase, which is good. And again, we could come back and find what's going on in the blanket. We're going to solve the general diffusion equation. Looking at the blanket. Again, the general diffusion equation still holds. We know that at the intersection point here, that the flux in the blanket has to exactly equal the flux in the core because you can't have a discontinuity. If we follow this, it's going to go out here where the flux goes to 0. It's going to have a little d. This little d is a function of materials in the blanket. And then we go back and use the same boundary and initial conditions to solve everything. And again, you're going to have a set of two simultaneous equations. You're going to have the flux in the core, and you're going to have the flux in the blanket. And you can solve those simultaneously to see what's going on within your system. I think if you stop and think about this, the next step up might be what? Having both a blanket and a reflector. And if you did that, you typically put the blanket immediately around the bare core because you want to take advantage of these neutrons when they leave, creating either a thermal fission and or scattering back. And then you put around that I hate these things. Okay. So now when something leaks out of here, it can go in here and cause a fission or get scattered back. When it goes through here, it could be scattered back in again to cause a fission, etc. So both of these are good. And this time you're going to have a flux in the core, a flux in the blanket, and a flux in the reflector. Then you're going to end up with a set of three simultaneous equations that you have to solve, and you're going to use these for boundary and initial conditions. For example, if I look at this point right here, I know that exactly at this point between the interface, that the flux in the blanket has to exactly equal the flux in the reflector because we can't have a discontinuity. This flux, when it goes outside the reflector, is going to go to 0. It's going to have a little extrapolation distance. This distance is a function of the reflector material. The flux is still going to have its largest value on the center line. The slope at the center line is still going to be 0 as one of our boundary initial conditions. So the more, and you could have multiples. You could have a blanket, another reflector, another reflector. It depends on what you're trying to do ultimately with your flux inside the bare core. If we have a little time on Monday before the exam, I might talk about the next step up, because remember, all of this is looking at just thermal neutrons or one group theory. So the next step up is two group theory. And I've talked a little bit about that, where we have thermal, and then we lump all the epithermal and fast together. So each one of those will have a flux. So if you're inside here, inside the bare core, and you're doing two group theory, you're gonna have a flux associated with thermal. You're also gonna have a flux associated with, I'll just call it epithermal. So the more you go, whether you're looking at blankets, reflectors, remember an average commercial nuclear reactor has 17 group theory. So there is some heavy duty math going on to understand what's going on with fluxes, neutron current densities, all that type of thing. I just wanted to give you a little bit of an overview on that. Okay, why don't we take a break? I've got about 6 of 2. Why don't we come back at 5 after 2? We're going to do the solution to the nuclear materials science quiz that I gave you. And again, if anybody wants to put theirs up for extra credit, that would be great with me. Otherwise, we'll put mine up. Any quick questions? Okay, if not, I will see you in at 5 after. Okay, do I have any volunteers to put up the quiz, their quiz? No, okay. So, I have sketched up on the board what the cross section looks like. And then I've shown the multi-axis bending that we're applying to our system. Okay? So, the first thing I would do is look at this multi-axial bending and break this down into a vector acting in each direction. So if I look at this, I can make this vector be one that goes in that direction. And if I do, looking at this 35 degrees and the value magnitude of that vector, this vector is 14,000 times the cosine of 35 Newton meters. I know that if I let my thumb run along that axis, that defines the neutral axis for this moment. So if I come up here, I'm not sure where it's going to be yet, but I know it's going to go in that direction because that's the direction of my thumb. This is neutral axis 1. If I then let my finger curl, and remember, let your thumb go along the direction of the neutral axis. Curl your fingers, right hand rule, sit on your left hand. Don't even bring that out. Right hand rule, it curls towards compression. So I know that my neutral axis is in this direction. I have compression up there, so therefore I have to have tension down here. I then look at the other vector resolution. So this one, I have to be going in this direction with my curl like that. This one is going to be 14,000 times the sine of 35 degrees Newton meters. Again, I let my thumb go along the direction of travel. So this is going to define my neutral axis 2, just like this one was neutral axis 1. And I'm going to have to calculate where it is, but I know it's going to be going something like this, where this is neutral axis 2, neutral axis 1. I then, knowing that this is my neutral axis, I let my fingers, right hand rule, curl towards compression. So in this case, compression is on this side, tension is on that side. So when you look at this, this neutral axis, anything that's down in here this part is going to be tension, this part is going to be tension. So this side is always going to be positive for this particular case. If I look at this, anything above here, anything to the right of here is compression. So anything up here is going to be a minus stress. Therefore, anything down in here, this is going to be a positive contribution, but this is going to be a negative contribution. So you don't know which way that's going to go. On this one, anything above is compression. Anything this direction is tension. So anything in this area is also questionable until you solve it. So the next thing we need to do, let's go back to neutral axis 1. And we know we're going to need a neutral axis 1. We also know we're going to need a rectangular moment of inertia with that. the nice guy that I am, I gave you the same problem for the last couple of times. So we've already worked all this. So we know the neutral axis was 6.04 centimeters. And the rectangular moment of inertia was 1368 times 10 to the minus 8 meters to the fourth. Or if you wanted to be consistent here, I can make this times 10 to the minus 2 meters. Okay? Once you've calculated that, and we know that the neutral axis is equal to the sum of areas times their centroids divided by the sum of areas. In this case, we had a semicircle, a rectangle, and a triangle. Up here, also down here, and we had this value come out to be this. The next thing I would do is go back in, label that neutral axis, because we've used this as our baseline. So the value that we found from the baseline to the neutral axis was 6.02 centimeters. When we did the rectangular moment of inertia, we know the rectangular moment of inertia is equal to the sum of the individual rectangular moment of inertia for that shape plus the area of that shape times d squared. We're going to have to do this calculation for however many number of segments we have. So again, 1, 2, 3. And this d squared again, because in looking at some of your quizzes, you're missing the point here. D is defined as the distance between the neutral axis and the centroid of that one shape that you're doing this calculation on. And although I didn't write it in here, it is the straight line distance. So all of this we had done in previous quizzes. So you didn't have to recalculate this. If you were glutton for punishment or you wanted to practice, you could have done it again. And hopefully you came up with the same answers. We then needed to come up with neutral axis 2 and its total rectangular moment of inertia. To do that, we need to rotate this shape 90 degrees. Doesn't make any difference. You could rotate it 90 degrees that way. You could rotate it 90 degrees that way. I happen to rotate it this way. So the new shape I had looked like this. You typically select the lowest spot to be your baseline. So you'll always have positive numbers you're working from. Could you have picked something else? Could you have picked this line right here? Sure. Could you have picked this line right here? Sure. But when you do that, you tend to get confused about various distances and values. You're still going to come up with the same answer, but you tend to confuse yourself. Now, if you were smart enough to look at this and say, you know, this thing is symmetrical, and if it's symmetrical, then that neutral axis is going to go right down the middle of this thing. And this neutral axis is going to be 5 centimeters high. So this neutral axis is from the baseline (5 centimeters) to neutral axis 2. But you could also say, maybe I need to do this just for validation or to prove that I can calculate this. So I could look at the neutral axis is the sum of my areas times my centroids divided by the sum of areas. So if I look at this guy, its area is 1/2 pi r squared. Its centroid from the baseline to here is 5. Plus this area is 2 times 6. To its centroid is also 5. Plus this guy is 1/2 the base times the height times its centroid is 5. Go back, divided by the area is 1/2 pi r squared plus 2 times 6 plus 1/2 the base, which is 2 times 6, excuse me. 8 times 4, might as well throw these numbers in here. And lo and behold, when you do this math, this guy comes out to be exactly 5 centimeters.
So, Professor, when you're dealing with a shape like that, like a semicircle that's sideways, is there some equation to use to find that value of 5, or is it just kind of you have to look at it and know that?
To find the value of what, Sarah?
So, to find the centroid is at 5. Is there some equation that you can use? Because I tried a bunch of them and I couldn't quite figure out if you just look at it. So, I mean, I understand where it is. I just didn't know if you just say it's 5 or if there's some equation to find that.
All I would say is if you look on the second page of the handout that I sent to you a long time ago, and you look at these and they talk about an X bar, a Y bar, and an area for each shape. And it's all based around where a capital O is or a 0, that they're taking all those values. So when you look at that, when you're finding the centroid, you could hopefully look at this and see it's exactly in the middle. And if you go over the value for X is 0, which means it's on that line. But when you look at that, you could say this area is exactly equal to that area, and that defines the centroid. So the centroid is going to be along that line. Actually, it's going to be right there if you use that other calculation, the 3h over 5. It's actually going to be right here, but what you're concerned about is that distance. It's like when you're doing the rectangle, when you did it here, you know half of 6 is 3, so you know it's going to be 3, so you know it's going to be somewhere along that line, and you need to find the distance from the baseline there. And again, 1 this way, 1 this way, so that distance is also going to be 5. When you look at this one, it's the same type of thing. You know that it's going to be on this line, and for a triangle, it is what? H over 3. So this value is H over 3 in this direction. But when you look at it for this direction, it's along this line, and that line is 5 from the baseline. So they might not have printed everything on this table, but hopefully it is self-apparent.
Yep, that makes sense. Thank you.
So, any questions on that? Okay. Let me erase this. So you got my neutral axis here is 5 centimeters, or 5 times 10 to the minus 2 meters. Now I need to find I2. We know that's a sum of I sub 0 plus AD squareds. Okay? So, doesn't make any difference which order you do them in. I did the triangle first. So I sub 0 for that is 1/36 the base times the height cubed plus the area, which is 1/2 the base times the height times d, and d is the distance from the centroid to the neutral axis. So it's 5 minus 5, so this is 0. 0 squared is still 0. 0 times this takes care of that. So my base here was 4. My height cubed was 8 cubed. And again, we're going back and looking at this orientation. So this is 4. My height is 8. I'm now going to go back and do the same thing for my rectangle. We know that's 1/12 the base times the height cubed times the area, which is the base times the height, times d. And again, the distance from the neutral axis to its centroid is 5 minus 5, or exactly 0. 0 squared is 0. 0 times this is still 0. So in this case, the base was 6. The height was 2 that we're going to cube. I don't know if you can see below this, so I'm going to just move over here. So the next one was the semicircle. And the semicircle for I sub 0 is 1/8 pi times r to the 4th. My radius is 5. Plus the area, which is 1/2 pi times r squared times d squared. But what is d? D is the distance from the neutral axis to its centroid. 5 minus 5 is 0. So this is 0 squared, which is 0 times this is 0. So it's plus 1/8 pi r to the 4th, where that value for r is 5. And again, where did I get this? I got this off the 3rd page of the handout that I gave you. So for those values I came up with, and I'm going to slide this over here, I got, for the triangle, I had that value to be 56.89. For the rectangle, I got 4.0. And for the semicircle, I got 245.44. So when I added all those up, I got 306.33 times 10 to the minus 8 meters to the 4th. So I now know this guy okay. So now I have everything I need to go back and look at finding out the stresses at those points of interest. Any questions on what I've done so far? If you've noticed, the fingers never left the hand on any of those calculations. Everything was above board. Okay.
Yeah, can I just ask a question about, so on the handout that you gave us, there's an IX value and an IY value. When would I go to the IY value?
Okay. You look at where the centroid is that they're taking the value around. So when you take it at the top, you see the X prime is going through the C for the rectangle. So you're going to use the very first one, which is 1/12 BH cubed. You drop down to the triangle, you see that the X prime again goes through the C, which is the centroid. If you go over here, you again use the first one, which is 1/36 the base times the height cubed. if you look at the circle, again, we're looking at the rectangular moment of inertia, not the one below it, which is the polar moment of inertia. So that oneself. Then the same thing here for the semicircle. In this case, they're equal. 1/8 I r to the 4th. If you have a quarter circle, again, you look at where that C is, and the value you're going to use there is 1/16 I r to the 4th. If you have an ellipse, again, look to see where the 0 is. So we're going to use the top one, which is 1/4 pi. And then if you look at A is so this is an ellipse. So you know that A is not equal to B. And what it tells you is for that orientation, my I sub 0 value is 1/4 AB cubed. And if you notice down before, this is what the A value is. So if this dimension was 10, my A value is 5. If this dimension is 8, this dimension B is 4 cubed. Okay. Although it doesn't show it there, what would I be if I gave you a just the upper half of this, a semi-ellipse? What would that I sub 0 be for that? The semi-ellipse is 1/2 the area of a full ellipse. So I divide this by 2, so that value would be 1/8 AB. So I could give you, or you could look at any strange shape, look at these basic definitions, and go accordingly. If you follow, that's how they went from a circle to a semicircle to a quarter circle, by using that same logic technique. Anything else, Todd?
No, I think that covers it. Thank you.
Okay, so now we're ready to rock and roll. So here we have the information we need. Now we go back and say, what points was he asking about? So we had point R, which was right there. Point Q that is right there. So I've asked you, what is the plane stress at point R? We know that by the principle of superposition, we can take the contribution of each moment and add them together. So this is M1 Y1 divided by I1. That's a contribution from one moment. And then we're going to add to that the second moment contribution. So these are unique to the first one. These are unique to the second one. So let's go back and fill in some values right away that we know about. Okay. We know that this moment 1 relates to this neutral axis and this centroid. So that M was 11468.13 meters. And what was that? That was 14,000 times the cosine of 35 degrees. What is I1? I1 is what we've calculated up here, which is 1368 times 10 to the minus 8 meters to the fourth. Might as well throw in everything that we know right now. So this guy was the 14,000 times the sine of 35. So that guy was, come out wherever you are, 8,030.07 Newton meters, which is this. Notice I haven't put any plus or minus signs. We're not going to do that till the very end. What is the rectangular moment of inertia for this relationship? It is this guy. Okay. Now we're going to go and find out the values for y. Y is the straight line distance from the neutral axis to the point of interest. Okay? This is my neutral axis. This is the centroid, 6.02. This is the baseline. So what I'm interested in is the distance from this neutral axis to the point of interest. What is that? You might be able to calculate it in your head, but probably the easiest way to do it is say, if I go from the baseline up to here is 5 plus 6 is 11. From the baseline to the neutral axis is 6.02. And again, this is times 10 to the minus 2 meters. Now I look at the sine. Everything above the neutral axis is in compression. So this contribution is negative. I then look at this guy. My neutral axis is going in this direction, which goes directly down the middle of the rectangle. So the distance from that neutral axis to the point of interest is that little distance. That little distance is half of 2, so that is exactly 1. Okay. Any questions on what I did? I then do the math on this. I had this guy come out to be minus 41.58. This guy come out to be plus 26.21. So my net result is minus 15.37 megapascals, because again, 10 to the minus 2 divided by 10 to the minus 8 will give us 10 to the 6, which is mega. And then because we have everything in newtons and meters, it's going to come out pascals. Any questions on that? All right, if we do the last one, and now I'm looking at point Q, so I'm going to change this to Q, okay? We'll determine the signs of this later. So when we start again, does M1 change? No. Does I1 change? No, because they're a function of the properties of this cross-section with this defined neutral axis and baseline. Does M2 or I2 change? No, because they're a function of the neutral axis on the rotated shape with its unique baseline. So this value, this value, this value, and this value all stay the same. Now we have to go see what are the y's associated with that one. Okay. So if we look at the first one, y is 1 is a distance from the neutral axis to the point of interest. And again, that's why it's nice to have a baseline, because you can use your baseline to count. So from the baseline to the neutral axis is 6.02. From the baseline to the point in question is 5. So that distance times 10 to the minus 2 meters, this is 6.02 minus 5 times 10 to the minus 2 meters. Okay. We then look at this section, and it says, what is the distance from the neutral axis to the point of interest? This is the neutral axis. We have to go this direction, and that's 5. Okay. Now we have to throw in our signs. Okay. If we look at this guy, this point is below this neutral axis. Everything below the neutral axis is in tension. That sign is positive. If we look at this neutral axis, the points here, everything on this side of the neutral axis is also in tension. So that value is also plus. So for this value, I got 8.72. For this value, I got plus 131.07. So I had the total be 139.79 megapascals, and the sign was plus. And we could find it anywhere. Let's say you wanted to find out let's invent a new point called V. And let's make V two centimeters in that direction, down 2 centimeters, and this is point V. Okay. Could I ask you, what is the plane stress at V? And the answer is absolutely yes. So let's go back. We're going to go back and still use the same stress equation for multiple bending. We're going to use the principle of superposition. And again, you've already done the heavy lifting, so you know M1 does not change, I1 does not change, M2 does not change, I2 does not change. Okay. So what we have to find now, let me just erase these signs here so we don't get confused. So what about the sign? For V, okay, Y1 is the distance from the neutral axis in this orientation to the point of interest. Okay, that's this neutral axis. So we're looking for the distance from the neutral axis to that point. If this is 2 centimeters down, this is 5, this is 3 centimeters up. So this is to here is 6.02, okay? And this distance up from the base is what? 3. So this distance from the neutral axis to here is 6.02 minus 3. So that's going to be 3.02 times 10 to the minus 2 meters. We'll do the signs at the end. Now let's look at the other orientation. What is Y2? Y2 is a distance from the neutral axis to the point of interest. So in this case, it's here, but we're going out from this neutral axis, exactly 2. So this value is 2. Now let's go back and look at the signs. For point V, for this neutral axis, this point is below the neutral axis. Everything below this neutral axis is a tension. So this calculation, when you do it, is a plus. If we look at V in this representation, this is to this side of the neutral axis. Everything on this side of the neutral axis is in compression. So this calculation is going to be minus. So when you do your math, this guy is going to be plus, this guy is going to be minus. So until you do the math, you don't know whether your final answer is going to be positive or negative, but you know you're going to have an additive or a tensile part and a compressive part. Okay. And then the final question for extra credit was, where is the plane stress exactly equal to 0? The neutral axis, which remember is actually a plane, is where the plane stress is 0 for this orientation. When we rotated it, this neutral axis, which is also a plane, defines where the plane stress is 0. So where this neutral axis exactly meets this neutral axis, which is right here, in this view, that point, if we call this point P, the plane stress at point P is exactly 0 because it lies on the two neutral axes. If you actually rotated this 90 degrees, this dot actually becomes a straight line where the stress is equal to 0. But all we're looking at is this view. So it's at that point, which is going to be 6.02 centimeters up from that baseline, 5 centimeters over from that baseline. Exactly that point is where the stress is equal to 0. And that was the quiz. Okay? So, on the exam, which will be in class on Monday, I'm going to give you a multi-axial bending moment. And I will probably give you, haven't made it up yet. I may going to make it up later today, or I'll do it tomorrow while I'm at URI. I'll probably get 3, 4, or 5 shapes put together. Okay. Any questions on what we did for this? The only other thing we talked about was whenever you calculate this value, whether you did it for R or Q or V or whatever, we can always go back and look at safety by comparing the stress at any point versus the yield for the material. Notice in this case, I never told you what the material was. Did anybody try to do the extra credit? Okay. In that particular case, I told you the system is made out of aluminum 1100. And we know the yield value for that was 95 megapascals. Okay. So the problem with that is, or when you go to do that calculation, is we know that this maximum value is going to have a maximum for tension, and it's going to have a maximum for compression. In this particular case, if everything to the right of here is in compression, everything above is in compression, we have to find that one point where sigma max for compression exists, If you did it, it's going to be somewhere along the line of that side of the triangle. That is difficult to calculate. That's why I gave you the extra credit to try to do that. Likewise, if I looked at the tensile, you know it has to be below this neutral axis and this way, and it's also going to be somewhere on the circumference of that semicircle. That is difficult to find. That's why I gave you the extra credit. But let's say you did find this point, and that point was, this distance was 3.3 centimeters, and this distance up was 2.2 centimeters. So I now know the maximum value of tension. I could find the maximum value of tension. This stays the same, this stays the same, this stays the same, this stays the same. I have to find y, and y is the distance from this neutral axis to that point, which is going to be 6.02 minus 2.2, and it's going to be plus because this is tensile. For this y, it's a distance from this neutral axis to here. So if this distance is 3.3, it's going to be 3.3. And again, this value be plus because it's tensile. So doing this part of it is fairly easy. It's finding out where this actual point is, where the maximum value is for either compression or tension. Anything else you want to go over for the exam on Monday? My guess is right now I'll probably lecture for or catch up on stuff for like 15 minutes, no more than half an hour, and then I will, and during that time I'll also give you your take-home reactor theory. I'll go over it with you to make sure you understand it. And then I'll go over your nuclear material science. And you'll have that no later than 1, and then you have till 3:15 to do it. Anything else you want to review today? We had gone through before what happens if you have multiple materials, and all you do is change the widths by whatever common denominator material you choose to work with. I could start into the next section. I might just mention the next section we're going to discuss, which are cantilever beams. I'll just spend 5 minutes going over that in general, just a general overview, and then we'll probably pick up on that once we come back from Thanksgiving. Any final questions for review for nuclear material science exam on Monday?
Can you talk a little bit again about using multiple materials in like
Okay.
Yeah.
All right. I won't do this one again. I'll pick a different one. Okay. This is actually a semicircle. Okay. And this is a semi-ellipse. Okay. And let's say this is material 1, this is material 2, this is material 3, and this is material 4. And you find out that material 4, the E value is for the 3 guy. Values. So this is 4. This is 3. Two. And this is 1.
And that's a value of 6 in the semicircle?
This guy is 2 by 8.
No, I know, the
This
semicircle.
Yes. This is 3, 3, 3. 4, region 3. This is a semi-ellipse, which is 3 by 8. And this top is another rectangle, which is 2 by 10. So let me re-sketch this over here. A little less messy. So this guy is 2, this guy is 8. This is 3, this is 3, this is 3 for my semicircle. This is 3. That's 8 for my semi-ellipse. And then the top is 2 times 10. Okay. And we know we have sections 1, 2, 3, and 4. So whenever you do this, you pick a common denominator, and then you make that cross-section be all that material. So in this case, I would pick E4. So I'm going to look at E4 to E4, E3 to E4, E2 to E4, and E1 to E4. So E4 is 50 divided by 50, so that's 1. E3 is 100 divided by 50, so that is 2. This is 150 divided by 50, so this is 3. This final one is 200 divided by 50, so this is 4. So whatever that ratio is, you multiply the widths only by the multiplier. Okay? So E4 is on top. Its multiplier is 1, so the top does not change. If we look at 3, which is this side, that multiplier was 2, and the width here is what? It is 3. So if I multiply 3 times the multiplier of 2, that is 6. So this new shape, instead of 3, is now 6. But we don't mess with the height. So my semicircle has become a semi-ellipse. If I look at my semi-ellipse, that multiplier is 3. So this was 3. We only changed the width. So this 3 now becomes 3 times 3, or 9. So it goes from a semi-ellipse to a different looking semi-ellipse. And then finally, my other one has a factor of 4. So this was 2. 2 times 4 is 8. So this becomes 8. So this doesn't show up very well, but this is now going to be 8 times 2. This side is 8. This side coming down doesn't change, so it's 8. I still didn't draw it right. Attached to the side here is going to be, this side is still going to be 6. This side is going to be 6. This side is still going to be 8. This side is now going to be 9. And this guy on top, the 10 times 2, still stays the same. So that's what the modified shape looks like. Then you'd use that to calculate the neutral axis for that shape, calculate the rectangular moment of inertia to that shape. And if we apply just one bending moment to it, we could find the stress anywhere and then compare that yield value for my basis, which was the E4 material, which is the guy on the top, to see if it fails anywhere. Okay. Any other questions for the exam? Okay, I'm going to probably spend 3 minutes just telling you what a cantilever beam is, and then we'll call it a day. Let's say we have a wall, and now we firmly affix our member to that wall. And if you want to think of this like a diving board, okay? And then let's say we apply a force here at the end. And if I look at the cross section on this, let's make it a T-bar. Where this is, let's say, 2 times 4 times 3 times 6, just to give it some dimensions. And we'll make this length 8 meters. What happens to this member when you apply that downward force at the end? This thing drops down. It stays fixed at this wall, but it drops down. And if you look at that, the top part lengthens, so it's in tension. The bottom part is actually compressed, and there is a point to where we have another neutral axis. We could find that neutral axis by looking at the sum of AY's, sum of A's. So we'll have a neutral axis here. If we translated that neutral axis over here, everything above this is in tension. Everything below that is in compression. But to really see what goes on, we're going to step back a couple weeks, we're going to have to do a complete free body diagram. So if I sketch the member, drawing any given forces, moments, torques, couples, the one I have is the force at the end. Okay. How many attachment points do I have? I have 1. So we know we can only add forces, moments, torques, couples at our attachment point. We're going to have to use the 6 equilibrium equations to see what's going on. We have the sum of forces has to equal 0. There are the 3 of those, x, y, and z. Hopefully you can see that the only thing in x, y, or z is in the y direction, so we have to have a force here at the wall going like that. But is that complete? No, because if you just look at that, this force going up, this force going down, it's going to make this member want to rotate clockwise. So for equilibrium, we can't have that. So that means if this is going clockwise, at the wall, we have to apply a moment that is counterclockwise to put it in equilibrium. We can find out what that is using the 6 equilibrium equations, so that when you go to look at safety here, you're going to have both plane stress because of the moment, and you're going to have shear stress due to the vertical forces. And actually, if this is a diving board and it's made up of, let's say, five individual pieces that you've glued together or nailed together, when you apply these forces, or in this case, a force, you could add other forces, these want to move relative to one another. And the movement could be enough to snap the nails in two or to break the glue apart. And just like we've had a vertical shear here, we could cut this and look at the upper half with a free body diagram. And you'll find out that there's actually a horizontal shear. And if we divide this by the area it's acting on, we have a shear stress. So we could actually have the system fail due to this horizontal shear, as well as the bending moment where it pulls out from the wall. We're going to start on this after we come back after Thanksgiving. So I will be around today to my usual probably 6 or 7 o'clock tonight. I'm going to try to grade your 2 quizzes today. So for the group that goes tomorrow, URI, I graded the last reactor theory quiz, and I'll grade these other 2, and I will hand them to the 12 of you that are attending tomorrow. If I don't finish up grading those 2 quizzes tonight, if I need tomorrow at URI, I'll ask one of the students there tomorrow who's coming in for the first electrical lab on Friday morning to bring back the 2 quizzes for the people that attended URI yesterday. So, you need to get back to me today. There's no quizzes or anything for Monday. And of course, going forward, there'll be no quizzes due the Monday after Thanksgiving. But we will have that one exam due on Wednesday. We'll finish up the other exam on Monday next week. So I'll be around today if I need you. I'll see the other 12 of you tomorrow at URI. Be ready to rock and roll at 10. Any quick questions? Sir, you had your microphone on?
Sorry.
Anybody else? Okay, have a good day.